basically serialization and deserialization to move data. Now this is almost done. Works everywhere, mostly on Chrome. It now works on Safari. It works on Firefox, but it's buggy. And also one of the things that is annoying is the off-screen canvas, because you want to be able to read directly in the back buffer before displaying it. That doesn't work anywhere correctly. And finally, the hardware decoder only works in Chrome for now. But maybe Firefox will do something one day.
Sorry, what's the total size of the payload that the page has to download to get that?
25 megabytes. So the idea is that we are going to, like, VLC is a module approach. So there is like a very small core and 400, 500, 600 now maybe modules. And so what I want is to actually be able to load, and that's almost working in theory. So you can load a shared object. So you would like only stream the core, and then the core will know which one to go and download. Yes, Steve. I'm not answering that question. Thank you.
You need to repeat it.
So the question was, when is FFmpeg community moving to a sane thing, which is GitLab? Not my Schultz, right? Like, you know my opinion, right? VideoLAN, VLC, all the iOS, Android ports, X264, and so on. Even David is on GitLab, and we like it. The FFmpeg community prefers to stay on email. So I think it's a mistake, because we are losing too many patches, because it's very difficult to, like, but that's the community opinion, and the community is a majority.
Last question.
So if you're rendering in OpenGL in the VLC.js, you're bypassing the media engine, right? So how do you do the audio-video sync?
Well, of course, so the answer is like, how are you doing audio-video synchronization? Well, like VLC, right? Like, the core of VLC was done by this guy and other guys to actually do, like, live TV, right? So the core of VLC is a clock, and the clock is basically working on doing like synchronization audio and video and resampling the audio when it's too late and so on. So here we are doing exactly that, right? So we output audio with web audio. A small part of web audio called audio worklets, and so we know how much is actually being played back, and then we control the vout, which is basically the core of VLC to synchronize audio and video, and we're using that there. But I'm not using any type of media source extension or any other open media, blah, blah, blah. We are really like, it's mostly a video game. Okay.
Thank you, Julie.
Et j'ai réussi à être à l'heure.
J'avais une question en ligne, mais tant pis, on n'a pas eu le temps.
Oh bah.
Désolé.
Bon, ça t'allait?
Ouais. Si t'as besoin de plus de temps, tu le dis, hein, tu sais.
Ouais, mais en fait, j'aime pas trop. Ça me prend trop de temps, c'est chiant. Je préfère torcher ça en une demi-heure. Ah oui. Je préfère torcher ça en une demi-heure. Je préfère faire ça en une demi-heure. De toute façon, après, c'est pour dire quoi de plus, quoi. C'est rentrer dans les détails, les gens, ils savent me contacter. Et après, c'est quoi? No, I think there is AV1 HDR right now, no?
Yes, VVT, tu sais qui c'est?
Oui.
Tu sais où il est? Ah, that's him.
I have uploaded the slides.
Yeah, I will do that. Can you put that here and this in your pocket?
All right, okay.
Est-ce que tu les as eus? Faut faire des
Est-ce que tu les as mis sur le site?
Je les ai envoyés par mail.
Mets-les sur le site ou à l'endroit où tu as fait la soumission. Tu peux les rajouter. Ça sera plus pratique pour moi parce que... Okay, thanks. Is there any check the sound before you leave?
Moi, j'avais pas vu de rester jusqu'à maintenant.
Can you speak for Kiran?
Hi, can you hear me?
That's your slides?
Yes, correct.
Then we'll make it single page. slideshow. So you can come here.
Yeah, just a moment.
You need water or something?
Probably that would be nice.
I forgot to.
Slideshow will automatically go.
No, you have to do
No, it was
right and left.
Yeah, okay. It was automatically panning with different slides. So okay, it's,
Yeah, right and left.
yeah. All right,
That's all you need.
all right, sure.
So what time is it? Almost there. We wait for one.
Yeah, forward one.
Yeah, 1 minute. So I should introduce you as Vibhuti.
Yeah, that's it.
Everybody is so silent.
We're waiting
I'm
for you
waiting
to tell
for-
the joke.
Sorry?
We're waiting for you
Oh,
to tell the joke.
I'm waiting for 1 p.m. We're there. So our next talk is about 4K video, HDR video with AV1. Please welcome Vibhuti.
Yeah, thanks. Hi everybody. So this is my first FOSDEM talk. So the main idea for this talk is that I just want to have a brief introduction about 4K HDR with AV1 and to know how it actually works. That's the main idea for the talk. And to give a brief introduction about myself, I am currently a PhD student in my second year, currently working on video coding, trying to learn how video works. And I'm also involved in open source multimedia since 2018, start with VideoLAN, Zip, and AOM media. So what are we going to do today? Okay, this picture was captured when we were trying to play multiple streams at the same time, 4K AV1 HDR stream. So this was some snapshot of that. So main idea is that we want to talk about the main technical challenges when we want to play back AV1 streams, which is in HDR, and to retain the same colors as such. That's the main idea for the talk, right? So before I get into that, I just want to have an introduction about HDR. We all heard about that, and there are multiple aspects of HDR right now which is happening. So first aspect of HDR is that let's break down into multiple parts. So first aspect is that it has brighter pixels. So here is a snapshot of an image which is tone mapped down to BT709 for display. So this is in SDR, even though the picture was in SDR. So what happens here is that you could see, I don't know if I can see the cursor. So somewhere here it's like super dark at like 1 nits, and somewhere here it is super bright at 1000 nits. So in theory the picture is at like 4000 nits, but our display is only capable of showing at 1000 nits. So that's captured at 1000. And on comparison, for a normal standard dynamic range images, it's usually in 100 to 200 nits, and flat panels, modern flat panels go like 500 nits or something like that. But in theory HDR can go up to 10,000 nits, but most of the displays can't do that. So second aspect of HDR is that it has more bits. So so this is a representation of same brightness in 8 bits in SDR and in HDR. So you could see that there is a lot of condensation happening when it is in SDR. So if you want to show or code something like 200 or 200 nits, you could get away with something like 8 bits. And when you want to go to something like 1000 nits, 8 bits is not we need more than 8 bits. So that's one aspect of HDR. So that means we need more bits. So what happened is that we need a mechanism to combine both nits and bits. So that's how this transfer function was born. So what happens is that our human eyes is quite sensitive to dark and mid-gray areas, and we are okay with bright spots. So with keeping this in mind, different standard bodies and organizations try to create something called transfer function, where they try to spend more amount of bits in the bright and low mid-gray areas and have a coarser quantization for bright areas. So that's how this transfer function is born. And in HDR, one of the common thing is perceptual quantization, PQ, which is based upon human perception of banding. So I'm not getting into details. So main idea of HDR transfer function is this, and there is multiple transfer function, but the core idea is that spend more bits on darker and mid-gray areas, right? Then comes the color. Color is complex. I don't know what the color is. So how to say is that to keep it simple and short. So display technology since standardization of HDR, which was like back in 90s or early 2000, it has evolved quite a lot, and now the display technologies is capable of displaying more brightness and more colors and things like that. So if you see this diagram here, right, so to keep it simple, what happens is that this shaded region is the standard dynamic range and SDR range. So that is this SDR, and what happens is that in HDR domain, or not in HDR, the white color gamut domain, it is expanded to be something like this, so it can have more wider colors. To have a quick background, so you remember the picture which we were talking earlier about, a picture which we are talking. So in this picture, when we actually check the color distribution of how it is actually spread out, so you could see this was manually measured with the help of a color library. So you could see that the trees and the green areas in the picture is actually beyond 709. So in this picture, you could see that this red triangle is the standard dynamic range in SDR, and the green one is the BT 2020. You could see that the greens is in the wider region. So the main idea, to keep it simple, is that there is reds and green have wider range, and blues do not change much. So that's why most of the HDR pictures and videos which you see might have vibrant colors with reds and green. That's one of the main reason for that, right? So now comes the question, where do you find these HDR sequences? Again, these are tone map sequences just for representation. So in practice or in reality, this may not be how it looks. So there are a bunch of sequences. Netflix has released some of the sequences as open content, which is available in public, and some other broadcasters have also published some of them, which is pretty good. And lately, maybe like early last year, Academy Software Foundation and partnered with American cinematographers also produced proper cinema grading material with different color spaces, which is also available. I haven't tested that. I found that like last week. Right, now let's come back to AV1. Right, so I had given a brief idea about HDR. Now talking about AV1, JB has given a brief idea about the current storyline of AV1 decoding. It's to have a quick refresher, so for people who didn't know, so AV1 is a current video coding standard developed from Alliance for Open Media around 2018, and it claims to be around 30 to 50% more efficient over predecessors, and that's around 200k lines. So it was an old number which I wrote. So for the video decoding and playback, David was there. So David is quite popular from Videoland, released that, and even major browsers and also operating system supports that, including Apple. Yeah, I don't know how to use AV1 in Apple. No, I don't know if anyone was able to actually use AV1 in Apple, even though Apple ships that. So that's the storyline. So that sounds good. So what's the actual problem when it comes to HDR and AV1? We see that it's able to play back and things like that. So the problem is playing back signals, playing back HDR videos with correct metadata and signaling them correctly on a display is not actually easy. So if we break down into three, first part is like the macOS. We know that the display support is there, latest macOS has the support, the OS is having support for signaling that, that's good. But the problem is video output drivers and playback natively in macOS is a bit problematic, and most of the players try to do tone mapping, and others have support, but they are very limited, so you may not be able to actually visualize them as you want. And in Linux, I believe we can't do because protocols are still work in progress. And in Windows, if we see that there is display and OS level support, and also players do support that with the help of DirectX drivers. So we could drive HDR playback in Windows and it works fine. But the problem I noticed mainly was like the display transition is there. When you play an HDR window, Windows try to flip from SDR to HDR. That takes few seconds and sometimes some black screen. So that's a problem which I noticed when you try to do in Windows. So that's a problematic thing which I noticed. So what we did is that we took a different approach. So this is kind of known to many people, probably most of the people in this room. So but we took this is the most common approach used in broadcast and standardization body industry. So that we are just using playback cards to play the video streams, and we are using a black cards from the Blackmagic. We use something called Decoding 8K Pro, so it can play the streams with, and it can send these signals with the help of SDI as output. And to play them, we are using FFmpeg and GStreamer for driving the playback, so we can work in any operating system if there is SDK support for that. So that's good. So we found a solution for playback. Now comes to the question like, how do you display that? So first thing is that we need to display this HDR signal with little to no changes. So with the playback card, we can send the signal. That's good. Then we need to make sure that the TV is not doing any sort of funky things during the playback, because most of the TVs sometimes tend to do some sort of tone mapping or try to play with the brightness and things based upon the ambient display. So we need to make sure that there is no sort of tone mapping and TV is not playing with that. And it should be calibrated as per standard. So that's the other thing, and it should have minimum of 1000 nits brightness. So that's the main requirement which we have for HDR testing, right? So what we went is that we went to the reference monitor. So we use something called Sony's reference monitor. So that's a 32-inch OLED panel that's strictly calibrated as per the standard, and it ticks all the boxes which we want. And even you can force the signal metadata on the playback. So that's good, even though that's an expensive guy. So the main idea with the reference monitor is that once we establish playback with HDR, we know that this is the source of truth or ground truth which we have. Once we do that, we can now show that this is how it actually look. Then we can extend to normal consumer displays which says to have HDR support, right? So that's good. Now how do we say that the signal and video which we play is actually HDR, or how do we say that that's the actual thing, right? So we need to confirm that thing. So first thing is that we need to confirm the brightness part, and so for the confirming the brightness part, we are using the European broadcasters has released a chart called EOTF chart, so which is going from 0 to 1000 nits. You won't be able to see that here anyway. So the idea here is that, so with this chart, if you play back in your stream, you could see the peak brightness which is available in your display. So that's the first part which for confirmation for the streams. The second part which we need to test is that what's the viewing area which you are able to see that. So if you're playing in a consumer TVs, some TVs says that they may have something like 4500 nits. So in theory that 4500 nits, in practice that 4500 nits might be only for like 2% area for few minutes or few seconds of your whole screen, and it goes back to something like 2000 nits or 1500 nits on other times. So we need to be sure that what's the actual area which we are able to show that. So that's one thing we can use this. So European broadcasters again release bunch of test patterns which you can confirm the maximum viewing area. So next comes that to confirm the signal which you are sending from the screen is okay or not. So for that we are just using a cross converter monitor which just check the existence of the signal. You pass through the signal through this, and it just says what the signal which you are sending is okay or not. This is just to make sure that the cables which you send and is correct or not, because sometimes cable can mess with you. So that's one thing which you can try. Then comes the color. This is the most important, because it can play a lot of tricks to you and you don't know what's this ground truth, right? So for that, in the reference, if you have the privilege of reference monitor, then the reference monitor has such settings called gamma marker. So it's actually essentially gives us like something like a zebra line on top of the screen if it is above 709. That's the main idea. But we may not be having reference monitor all the time, right? So we need some other mechanism to validate this thing. So we tried to use something called spectroradiometer. So this is a device which is used to measure something called radiance from the screen. So with this device we can measure the color volume, that is the color space and also the brightness. So with this device we can just point to the screen which we are playing the stream, and we know that this area might be in HDR. So once we point to the screen and measure the color, we can know that whether this is in HDR space and is the pixel above 709 or not, and what's the actual brightness which we are seeing, and things like that. Based upon the brightness, it varies. Brightness varies in the sense like the time it takes to capture that, it varies. So next important part is that the making sure the whole pipeline which you are using is in 10-bit. So this is a very important thing which might be a bit tricky to see in real life, because most of the, to give a background, right? So if you have a, so to make this easier, so the main idea here is that we make a custom coded 10-bit image having 1024 levels of the brightness. So once you send that, and if the whole pipeline is in 10-bit, you won't be seeing band and you will be having a smooth gradient. And if it is not in 10-bit, you may see some ramps here like this. It's not visible here, so essentially you will see some ramps here. So when in practice, when you send a signal, and if you try to do in consumer displays, even if you may even get the color volume and brightness and things like that, but it can be still in 8 bits. That what I'm talking is like it can be an 8-bit PQ. It's a real thing. I didn't know that before starting this. So with this you can be sure. The reason for saying this is that if you have some noise in your signal, and due to TV's debanding and dithering algorithm and all the other things which I don't know what TV is doing, it can make the bands not visible, and it can be smooth as this 10-bit, even though the video might be in 8 bits. So that's the main things which we focus to say, that for testing the HDR things we need to do at least one of them for each of these things: brightness, signal, color, and bit depth. So next question comes up, that can we extend this to consumer displays? Yes, we can do that, because we now established the ground truth and it works. Then we can use an SDI to HDMI converter, then we can send the HD, we can play it in a normal consumer displays. But that comes to the question that whether the consumer TVs can actually signal the metadata, or whether this playback card or the FFmpeg drivers, which how you play, can actually transport the metadata. So in the TV, modern consumer TVs can force the HDR metadata, that's okay. And if you don't have that, there is some device which we found recently, but it's there in industry for many years, that's called Dr. HDMI. So this guy is like, you plug in HDMI and it will insert the HDR metadata how we want with the web server, and it's like, it's a magic device, I would say. And fun fact, it can even do Dolby Vision with 8K 60 FPS. It can even fake Dolby Vision metadata to the TV so that TV will be happy. And this device is like less than €200. So it actually works for consumer TVs and old TVs which just have HDR. This guy is magic. And most of the time, many people who do HDR demos have this in the background in NAB or IBC. So that's one part. Now there comes to the question that, is this okay for HDR? So with the HDR, right, the viewing environment is crazy. So that's one thing, and based upon the viewing environment, you have different perception of colors. So main things here is that you just need to be sure that what's the display panel technology which you are using. Like I mentioned, previous test would be happy for that. You can have some sort of confidence with that. Then comes the ambient lighting condition on how you view that. If your room is getting dark, and based upon your ambient lighting, this varies. So you need to be sure what's the lighting in your room when you're watching the HDR videos. And again, video materials plays an important role. And lastly, perception of color. Different people have different tolerance of color. So that's one thing. And last important fact which I need to talk is that based upon viewing environment, and certain individuals can experience fatigue and dizziness when you watch HDR. That's a true thing. And because of the super bright and super vivid colors, you need to be careful when you are watching HDR videos for a long time. So ITU has laid out some methodology when you do this for scientific testing and subjective testing environment. It's not strictly written for HDR, but if you follow that, it works. On big picture, just keep it under 30 minutes when you watch HDR videos continuously. So this is some snapshot of how these set up scientific testing environment which we went, and when we had a person to view that, this is how it happened. So yeah, so the main things what I was talking here is that HDR signaling HDR metadata and things are different, and one of the main two things of HDR is that there is wide range of brightness due to different quantization scheme, and white color gamut, this was an entirely different concept. Now the current HDR videos and things has clubbed together, and that's this current standard says, so that enhance the colors. And last thing is that setting up the whole a subjective testing environment and things, or scientific testing environment is non-trivial, and it's accompanied by high cost, even though this is standard back in like 10 years back, the whole HDR. And the viewing environment plays an important role. Currently we are doing some set of subjective tests for HDR viewing and things like that. So I have put some references if you like to read more, and that's it. Thanks. Would we like to hear more questions? And I'm still learning these things, so I could be wrong. Please correct me if there is anything wrong.
Any question in the room?
Can you bring up the previous view? Yeah, thank you.
You have the slides also on FOSDEM website.
Okay.
All the slides.
Yeah, and also I have put some additional resources how you can do these things, some more information which I skipped in this thing. Yes.
I only have a little background in video codecs. Could you explain simply what the pipeline is you were mentioning? What does it do?
Not sure which pipeline are you
Much of the 10-bit pipeline, I believe.
okay, this one. Right, so this one you're talking. So what happens here, so what here I'm trying to convey is that the HDR videos, like I mentioned earlier, is coded in 10 bits or more than 10 bits. So the whole pipeline which you are trying to, so what have to boil down, so the TVs or some devices can decimate 2 bits and make it 8 bit when you play that. It can be, so you may see an HDR in 8 bits. So when you have it in 8 bits, the whole nature of HDR, in 8 bits you can represent 1000 nits brightness. So HDR having like quite wide range of brightness, and when you have less bits, you can't actually view that. So you just, that's the one thing which I mentioned here. Yes.
Because HDR is 10 bits right now, but there are plans to make it 12 bits in the future.
Yes.
So how are you going to extend your calibration and scientific testing equipment to cope with the extra 2 bits?
I don't know.
Can you repeat?
Yeah, so sorry, yeah. So he was asking like in future HDR might become 12 bits. So how am I going to extend this whole setup for 12 bits? I think that's after like 6 years, right? Yeah, so probably the capture.
Is it still 10 bits?
Already compliant with 12 bits.
Yeah, but in.
Both of them actually.
Yeah, okay, so probably, I think the capture card can do 12 bits, and probably, I probably would do something similar. I need to dig up how can we actually differentiate between 10 bit and 12 bits. I actually don't know.
Yeah, it's difficult to differentiate 10 bits already.
Yeah, 10 bits, yeah.
12 is going to be.
Yeah, it would be a bit tricky, but we'll find some way for sure.
Outside the display, you can put it into a waveform monitor. Like there are tools to look at the wire on the signal.
Yeah,
You see, look at the ramp and see the actual YE values.
yes.
Can you repeat what he says for
So-
the mic?
Alright, so he was suggesting we could use something like a waveform monitor to monitor the signal. Yeah, so that is part of something like this, and a more advanced device can have that. So this thing is like a cheap device, but even though it's $1,000. So this can show some waveforms. So yeah, he was suggesting we can use more advanced tools to show waveforms. Yeah.
Can you, so there is a method to repeat this setup in other places as well, so that you have a common reference system?
Yeah,
Rather
so-
than have exactly the same calibration.
So that's a tricky thing. So if you are repeating this for other setups, we just need to make sure that this for some of these things are like test patterns should be used to make sure the peak brightness is there and the maximum viewing area. Then we can use the spectroradiometer to make sure that the signal is in HDR, and to make sure that's okay. And I think this is repeatable in other places even if you don't have reference monitor, because we tried this on a normal consumer device with the same setup and it worked. Yes.
Why is AV1 best suited for HDR? Is it only because of the compression?
Yes, I would say so. And
Can you repeat what?
so sorry again. So he was suggesting why is AV1 better suited for HDR. So I don't know if AV1 is best suited for HDR also. It's one of the good codec which can do better compression. So natively it can do a lot of contents which is in a better quantization, and the things are bit better compared to other codecs, compared to predecessor codecs. And so due to that nature, it's okay to do HDR content, but still there is a lot of work to do in AV1 to be better compliant with HDR, because other codecs have way better handling for HDR, because most of the codecs right now, even though they have HDR, they don't treat the HDR signal or HDR videos differently. So it's still a research and development process currently which is happening in codec development to treat HDR differently, and everyone is slowly trying to do that.
What are these codecs?
So codecs in the sense like HEVC has some other extensions which can handle HDR in a different way with help of having different quantization for colors and things like that. AV1 is slowly so current AV1 master has that feature, I believe. So it's slowly in development, research and development process. All right.
We still have time for one or two questions. Yeah.
Is there a big difference in power consumption when a TV goes into HDR mode?
Yes. So the question he was asking is that whether the power consumption is higher in HDR or not. I actually didn't measure, but I know that when I play HDR and if I keep my hand on top of the screen, I can feel the heat. So the OLED is really burning. So if I keep like this distance, I can feel the heat in my hand. So it's really bad, I would say.
Another question?
My experience is when you play HDR, the picture actually becomes dark.
Yes. So he was asking why is it
that? Yeah.
why is it that more darker? So to answer that question, I was expecting this. I have some. So I was doing a subjective test for the same thing for a dark video with bunch of people. I didn't include that this requires more background and explanation to explain. So this was a dark image. So this is in HDR. So in actual setup and proper environment, you could see that clearly. But now this is purely washed out in blacks. So because on HDR it can do. Why is it like that? So I don't know, because in HDR you can spend more bits, right? So people tend to focus the importance of the dark videos and things like that. So I think it's just that you can exploit the wide range of luminance and brightness and quantization scheme of HDR when it is in dark. So what I'm here trying to show is that this is a bit complex to explain. So like the perception of this is very hard, and if you have a different lighting condition, the blacks and darks would be entirely different. So I think it's just the nature of content and they just want to utilize the HDR to be that. I'm not exactly sure how to answer that. I don't know. So like just like this, what I'm here trying to show is that even though you had different videos with different brightness and all, this is like a dark video, and when people try to view this in this environment, and when you have the worst compression and the best compression, people like these are different kind of noises. People just thought that they are same, even in the proper environment. So that's a whole different storyline. So it's a bit hard to answer why it is like that and how we can do that. Probably in another time I could explain this in a clear way. But I don't know. But yeah.
Well, thank you, Vibhuti.
Thanks.
If it's uploaded, I can put it there if you want. Just put on the mic to your shirt, somewhere around there, good, and this in your pocket.
Hi.
So if you
So left and right, quite simply. You want some water?
Yes. And you have the signs.
I have.
But I'm gonna
So
put.
it's 20 minutes plus 5 minutes questions.
Yeah.
So after 15 minutes, I will show you a sign saying there is only 5 minutes left.
Yes, nice to meet you.
And I'm gonna time myself too.
As you prefer. Yeah.
No, I mean do it, but you know, just.
I will show the sign anyway after 15 minutes. So, and that's all good.
Thanks.
So left and right. Just, you can.
If the talk has been already uploaded by me, it's fine enough for you because you can.
Slides, you mean?
Yeah.
If you upload it to Penta, then
Yes, it is.
then
They put it on public.
then it's public, and then I will download it.
So I don't need to do anything.
No, I think so. Now we're waiting for 1:30.
All right.
We don't start early because people watch us.
We're back on schedule again.
I think so, yeah. I will check if the mic is working because Kiran is going for lunch.
Very great people and everybody. Very serious. And you're suddenly you're working. You're like either somebody fast or even somebody really breathing through their
No. To talk? Or
Do you
just
hear?
talk?
Do you?
Then we're there, so I introduce you.
All right.
Remind me your name again. Adam?
Adam Wieczkowski. But you can just say Adam. It's all right.
Just
Sorry.
so many presenters.
No, sure.
So we continue with our next talk, again about codecs, this time about VVC, with two projects about encoding and decoding VVC. Please welcome Adam.
Hi everyone, so today I want to introduce you to VVEnc and VVDEC. Those are open source implementations for VVC. Now, to pick everyone up about VVC. So VVC is this new codec that was finalized just over 2 years ago. And if you want to know one thing about VVC, basically VVC allows you to have the same quality as HEVC at half the bitrate. And on top of that, it was developed by the JVET, which is the Joint Video Experts Group. And it's called versatile because it's applicable in versatile scenarios, right? So we have support for screen content, HDR, as we heard in the previous talk, immersive, 8K, and we can do some fancy stuff like doing adaptive streaming with OpenGOP. All right, so now let me talk you through a little bit of the background of our projects, VVDEC and VVEnc. So of course, those are both those are team efforts, right? They're developed by a whole team of researchers at the Fraunhofer HHI, mostly in the video coding systems group. Now, Fraunhofer HHI, if you don't know it, like modern video coding probably wouldn't be what it is if it wasn't for HHI. And HHI is part of a biggest European research organization, the Fraunhofer Society, which is a big German non-profit. And then about me, so I'm Adam Wieczkowski. I've been at HHI since 2016, and I've been leading the project since 2019. And since about a year, I'm also the co-head of the video coding systems group. So why did we even start the software project? So basically, there was HEVC for which the test model was HM, and HEVC uses square blocks. So they had this method of indexing blocks within the frames using this set index method, which is really amazing for square blocks. And then, they were exploring VVC based on the exploration model, which was still based on HM, except VVC supports rectangular blocks, right? So it's more than only square blocks, and there were really lots of code for working around this set index thingy. And at HHI, we wanted to do even more than that. So we started work on our own partitioner, and we just decided that this is not going to work. And what we had to do, we basically had to write our own software to deal with it, which we very creatively named the Next software, which later became the VTM 1.0. And basically, the biggest difference is we had one big map that was mapping the position within a frame to like an object that was describing the current coding block. So the next software, it became the VTM, which is the reference software for the VVC standard. And you can see there in the graph how the VTM was developing over time with regards to the gains over HM, with the encoding time, decoding time. And here you can also see how we started our implementation projects from VTM. So from the VTM 3.0, super early, we already started work on the VVDEC. And then from VTM 6.0, we started the work on VVEnc. Then in the early 2020, Benjamin Bros became my boss. Like we basically started the VCS group, and he brought up the idea maybe we can do the projects open source, which we did initially end of 2020 under a little bit shaky license, but with some back and forth with the headquarters, we were able to change it to like a modified BSD3 license, and after some more back and forth, we actually have an unmodified, like a standard open source license, the clear BSD3. All right, so let's talk some more about the projects. Some hard facts. So as I already mentioned, they are based off VTM. They are both written fully in C++, but we do have like a pure C interface, so you can integrate it into frameworks, or just use it from a pure C code. Those are C++ projects, right? So they are object-based, but it's very kept very simple. So we try to not hide anything, no getters, no setters, and like have all the control over what is happening in the memory. Contrary to some other, some other projects, we do not do assembler at all. We do only vectorization using intrinsics, which of course has the advantage that we get stuff like ARM support for free through this amazing SIMD everywhere library. Also support for WASM cross-compilation, so WebAssembly, which we also did. And what we try to do, we try to make those projects as simple as possible. So basically, we only expose options that are use case relevant, but like the coding options, everything that's like connected to efficiency, we try to define it for the user to just have the simplest experience possible. Yeah, they're both available on GitHub under the BSD3 clear license, as I already mentioned. All right, so how do we do the development? So the development is done internally without HHI. So we have our own main Git repo that we basically, from which we push squashed updates to the GitHub repo. Why is it internal? I know many people find it out a bit, there might be issues with that, but here on the right you can see, or maybe you cannot see, a typical merge request that I would do on the internal stuff, on the internal repo, and I think this is just not something that is ready to be released to the public, So I would rather, hide those kind of hiccups, and yeah, it just takes too much time to make stuff nice for being public. And I also think not everyone at HHI might be comfortable, being like a public developer. But yeah, all of the stuff that we have internally, it eventually goes to the public repo, either for new releases, to fix bugs or issues. If we develop a big new feature, we would push it. And if someone was to make a large contribution, of course, to rebase the code. All right, so VVDEC, the decoder project. So the highlights, it's fully compliant with the main 10 profile of VVC. Of course, give or take few bugs. So actually, it was supposed to be fully compliant since the version 1.0. But stuff happens, we find bugs, we fix the bugs. But basically, there is no feature that is really missing. It's multi-platform, so it works on all the major OSs. And it also works on different architectures, thanks to SIMD everywhere, as mentioned. So we have like x86 support, ARM. I also saw people, doing builds for RISC-V. So this is very nice. Also, one thing I'm kind of proud of also is that from the first version, we have like a unified thread pool. So also something that was already talked about. So basically, everything is, like all the tasks are collected within this one thread pool. That just balances itself, right? There is like no frame threads, slice threads, which also means our multi-threading is independent of bitstream features, right? We don't need tiles, slices to be able to parallelize. So I think this is a really nice feature. All right, let's look a little bit into the development history. So this on the left is like the performance graph for different resolutions, different coding conditions, so like random access or all intra. And major milestones mentioned 1.0, full compliance with the standard. In version 1.3, we did a 3 times memory reduction, and I was also asking myself, how could we ever release any other? How could we have ever released any other version? But yeah, at least we managed to get it better. 1.4, we got a major performance boost based off external contributions in GitHub, so this was really nice to see. And in between, we really had a lot of small improvements, and as you can see in the graphs, it does add up. All right, about the VV-enc. So VV-enc, it's a encoder project. Of course, it's way more complex, way more interesting. It has way more degrees of freedom, right? Like a decoder just does this one thing, and has 0 degree of freedom, right? Basically, the standard tells us exactly what to do, and the encoder has all of those choices that it has to do. Anyway, what I like to say is, it's basically the best open source encoder out there. As you can see here on the right, it's runtime versus efficiency. So, for a given runtime, we can have the best efficiency, and for any of our working points, we can get this efficiency the fastest. Of course, it's not the best encoder if you want to encode UHD live. We're not quite there yet. But, and at those slower working points, it really doesn't get better than that, at least not that I am aware of. All right, so we have 5 presets on the encoder, from faster to slower. And you can see, this is a single-threaded graph. You can see more or less how those presets compare to X265 in orange. We have very efficient multi-threading, at least between up to 8 threads or with up to 16 threads with some additional options. I'm going to talk about this a little bit in 2 slides. And we have very good optimization for human visual system based on the XPSNR metric, which I'm also going to mention a little bit later. We have really excellent rate control. So, with bitrate deviations, rarely more than 2%, and almost never more than 5%. As I mentioned, simple interface, and it's, this thing can be used for academic, amateur, commercial uses. The license really allows it all. All right, so we have those 5 presets. How do we derive those presets? From an academic point of view, this is actually done in a very interesting way. So we take all not use case related options of the encoder, and we do large scale optimization. So we start with a very simple, very fast working point, and then we try to derive which option should be changed as the next one. And this is always the option which basically gives incrementally the next best working point, right? And this is a huge optimization. It takes really a lot of compute time, so we don't do it so often, like every 2 or 3 versions. Or if we know one tool got implemented way better, we can try to only optimize for this tool within the option space from the last optimization. We target HD and UHD, natural content, but we do sanity checks for our resolution and screen content or HDR. And the one issue that we still have is, at the beginning here, you can see that our curve gets a little bit steeper, right? So we cannot go too fast, because at some point, for every 2 times speed up, we're just losing too much efficiency. This is because, we started from the reference software, which was designed for readability, and the efficiency is still work in progress. All right, about the multi-threading. So our multi-threading is also, I would say, done differently than in many other encoders. So we do the multi-threading over CTUs, so the modern macro blocks and CTU lines. We simulate wavefront parallel processing without using the syntax. And we parallelize independent frames, right? If 2 frames are independent of each other and the references are already done, we can do those in parallel. Which of course means that how much we can parallelize depends on the number of CTUs that are available, which are always more in high resolution or with smaller CTU sizes. That's why the faster and fast presets, which have smaller CTUs, they parallelize a little bit better, which you can see on the top right there in the full HD parallelization efficiency plot. Right, you can see after 8, it kind of, well, it doesn't saturate, but after 8 threads, there might be better ways to utilize the resources than to just enable more threads. Exactly, and how can we improve the scaling? So we can improve the scaling by enabling normative features of VVC. So either doing tiles, that is independent regions within the picture, or enabling the normative wavefront, which allows us to kill one dependency within the encoding. And this is on the bottom right. So you can see, if we enable those additional features, the multi-threading scaling actually gets much better, but it costs between 3 to 5% of bitrate overhead. But still, even with those added features, the encoder is not ready yet for more than, let's say, 32 threads. So like, if you have a really, really big server, the encoder will not be able to utilize all the cores. Yeah, and about our optimization for the human visual system, it's based on the XPSNR, which is this new metric that a colleague at HHI developed. It has a really high correlation with MOS based on some public data sets. There are publications you can look up. They're mentioned on the bottom left. And it has been contributed to FFmpeg as filter, and I think it is somewhere in the backlog of FFmpeg waiting to be looked at. You can see on the right here a lot of graphs. So basically, in the last JVET the JVET meeting one before last, there was a verification test with actual human subjects, where where VTM was tested with like the new compression technology, and we submitted VVENC to be tested alongside of it in the slow preset, right? So the slower preset has around the efficiency of VTM. Slow preset is objectively 5% behind. And as you can see in the graphs, VVENC in orange matches or outperforms VTM, which means that our visual optimization is well able to at least close this 5% gap, if not even add more in terms of visual, like subjective visual quality. So yeah, that's really nice. All right, VVENC in practice. Everyone asks in the end, so what kind of FPS can you achieve? So we did some encodes onto mobile workstation kind of computers, encodes using all defaults, which means 8 threads. And for HD versus live, it's like for faster, it's around ×4, like live ×4, so around 15 FPS. Medium around live times 30. All right, so around 2 FPS. I'm talking about HD 60 FPS as live. For UHD, the faster can do like 15 times live, fast 30, and medium, well, let's just say medium would only be of interest for like large-scale VOD encodings, right? But FPS also depends on many other factors like bitrate, content, your actual CPU and stuff like that. So this is more like ballpark numbers.
Excuse me, is this HDR content?
It is not HDR content, but it's 10-bit. So it should be roughly the same for HDR. Yeah, like we only test with 10-bit usually. It works for 8-bit, but it's kind of 10-bit native. All right, also some version history for the VVENC thing, for the VVENC project. So our first major milestone was the 0.3, where we added frame threading, and you can see on this multi-threaded efficiency versus speed graph that it was, a huge leap for us. In the 1.0, we added PureC interface, allowing, the integrations into PureC frameworks. 1.4, SynCat detection. 1.5, we added like arbitrary intra-period, so it doesn't have to be aligned to anything. We added a fast decode preset, and in the newest version, the thing that I really like about it is that we added the ARM support. And every version we add improved ray control, thanks also to great community feedback. And from one version to another, your encode might be 10% faster, but if you had a ray control problem and it got fixed, it's gonna be like way, way better. So this is like, this hard to quantify improvements are actually one of the most important ones. And you can see how the curve behaves. So extrapolating, I'm sure we're gonna get even faster and better in the future. All right, about the ecosystem and the community, of course, this is raw video encoding and decoding. This is really only of academic interest, right? Like, it doesn't really bring you anything. That's why we have been looking into FFmpeg support for a long time. There was an open access paper over 1.5 years ago that described how to do it for the decoder. There are some patches in the pipeline with FFmpeg. We also put in our wiki how to apply them manually if you want to build it. I know, I've talked about this a lot, but the thing is, if it's not in FFmpeg, it doesn't exist. That's why, we put up a how-to for you on how to do it. All right, about playback, once you get this FFmpeg with VVC included, you can just link whatever player uses FFmpeg as its backend, and it's going to work. As far as I know, for VLC, you might force it to use the FFmpeg as the demuxer. Not sure about it. Didn't test it myself. It comes from community feedback. I know there are some exoplayer integrations going around, which allow you to use it in Android apps more easily. We have a toy web browser example, but it's nothing like the VLC JS. It's really a toy example. And for maxing and demuxing, you can just use JPEG. Sorry, for maxing, dashing, you can just use JPEG since the version 2.0, and I think it also needs to be linked to an FFmpeg with VVC support. All right, for community, we are open to external contributions, and we wish to get some. That's also why I'm talking to you, to we'll get some interest. So we try to make this more easy by stating that the authors of VVEnc are also retain the copyright. We don't have like a contributors agreement, so this is like the only way we can make it happen. We are interested in all kinds of contributions, efficiency, speed up, and we're gonna thoroughly review this, test, generate result, whatever is needed, give proper feedback, merge. So yeah, please do if you're interested. To conclude.